If this furnace drifts just 10 degrees Celsius, every bottle shatters weeks later, even after passing inspection. Glass melts at 1,500 degrees Celsius, approximately 2,732 degrees Fahrenheit, but the real danger starts at 1,492 degrees. Drift 8 degrees too low, crystalline stones form. Drift too high, the furnace collapses. Here's the thermal battlefield that keeps molten glass alive. Glass bottles look simple, but each one survives 3 invisible systems. First, the batch. 99% pure silica sand mixed with soda ash and cullet, recycled glass, at 40 to 70% of the total. Adding cullet cuts energy use by 40%. Second, the melt. A 24-hour residence inside the furnace where controlled convection sweeps bubbles to the surface. Third, the forming line. Molten gobs drop at 1,100 degrees Celsius, approximately 2,012 degrees Fahrenheit, into molds, shaped by compressed air in under a second. Every year, billions of bottles move through this process. If any step drifts outside its window, the entire batch fails. Once the batch melts, the glass looks uniform, but invisible gas pockets remain trapped inside. The furnace holds the melt for 24 hours. Bubbles larger than 0.5 millimeters must be removed, or they cause optical defects and weak spots. Sodium sulfate fining agents release oxygen at high heat, creating microstreams that sweep voids to the surface. Controlled convection currents push lighter gas bubbles upward. Ultrasonic sensors scan the melt after homogenization. Thermal imaging tracks convection patterns in real time. If residence time drops below 20 hours, bubbles remain and cause defects. A single trapped bubble can refract light, making the bottle unsellable, or create a stress point that cracks under pressure. Extending residence time by 4 hours raises energy cost by 8%, but defect rates drop by over 30%, saving millions in rejected product. The melt appears still, but thermal cameras reveal constant motion. After 24 hours, ultrasonic sensors confirm bubble density has dropped below the threshold. Only then is the glass ready for forming. So the melt looks calm, but it's actually a 24-hour gas-purging marathon. 24 hours sounds slow, but rushing it leaves invisible bubbles that ruin clarity. The furnace runs continuously for years, but one 8-degree drift nucleates crystalline stones that fracture bottles. This is the part no one sees. The operating temperature is 1,500 degrees Celsius. The tolerance window is plus or minus 8 degrees. Gas flow is adjusted every 2 seconds. Thermal zones are mapped at plus or minus 3 degrees resolution. Regenerative burners recycle exhaust heat. Thermal imaging cameras are embedded in refractory walls. PID feedback loops adjust natural gas flow in real time. Here's what happens if they lose control. If temperature drifts by 10 degrees, crystalline stones form, hard mineral shards that freeze inside the melt and burst bottles under pressure. Stones are invisible in the melt, but catastrophic in the bottle. A single stone can cause a bottle to shatter during filling or transport. Regenerative burners recover up to 60% of exhaust heat. That cuts fuel consumption by 25% compared to conventional furnaces. This is the invisible system that keeps the glass from literally exploding. The furnace is a thermal battlefield. Regenerative burners preheat incoming air with outgoing exhaust, cycling every 20 minutes. Thermal cameras map every zone with plus or minus 3 degrees accuracy. PID loops react instantly, adjusting gas flow every 2 seconds to hold the plus or minus 8-degree window. Operators monitor remotely via SCADA, watching for drift. Heat is the enemy, and the only tool they have. The system is invisible to visitors, but it's the reason the furnace can run non-stop for 5 to 10 years between rebuilds. Since the ISO 7086 update in the 1990s, the tolerance tightened from plus or minus 12 degrees to plus or minus 8 degrees. Defect rates halved. A tiny drift and years of production go down. Plus or minus 8 degrees sounds tight, but drift by 10 degrees forms stones that crack bottles under pressure. Molten glass exits the furnace at 1,100 degrees Celsius. Shear blades cut it into gobs every 0.8 seconds. Each gob drops into a blank mold. The first blow of compressed air forms a parison, a hollow bubble. The parison transfers to the final mold. The second blow, at 6 to 8 bar, expands the glass against the mold walls, forming the bottle. The cycle repeats thousands of times per day. But here's the scary part. Each bottle looks solid now, but it's still full of internal stress. Fresh bottles enter the annealing tunnel. Temperature drops slowly from 500 degrees Celsius to 400 degrees over 20 to 30 minutes, relieving internal stress. If annealing is skipped or rushed, internal stress remains and bottles crack during filling. A bottle that passes forming but fails annealing can shatter in a customer's hand. And here's the insane part. At the exit, high-speed cameras inspect every bottle at over 1,000 per minute. Cracks, bubbles, or dimensional errors trigger automatic rejection. Rejected bottles are crushed and fed back as cullet. The loop closes with near-zero material waste. 1,000 plus bottles per minute inspected. Cameras catch flaws human eyes would miss in days. From 99% pure sand to a flawless bottle, the transformation depends on one invisible system. Thermal symmetry held within plus or minus 8 degrees by PID loops that adjust every 2 seconds. The furnace never stops, the glass never cools, and every flawless bottle you touch survived a 1,500-degree battlefield, and the most precise heat control system on Earth. Want to see the aluminum can line, where metal travels 60 kilometers per hour through dies, or the PET bottle stretch blow process next? Drop a comment.